Are you ready to learn about the hilarious subject of computability theory? An algorithm is a sequence of instructions followed by a computer. Now, you all think of computers as machines, but for an awful long time, what a computer meant was a person, the person who executed the algorithm. Algorithms go back to Euclid's Elements in classical Greece and to eponymously Al-Khwarizmi in 9th century Persia. But a formal mathematical definition doesn't appear until the 20th century, when you have proposals by Alonzo Church, Kurt Gödel, and Alan Turing, all appearing within a year of each other. It's like buses. You wait 2,000 years for a definition of effective computability, and then 3 come along at once. Why did this happen? So at the dawn of the 20th century, one of the foremost proponents of formal logic was David Hilbert in Göttingen. And what he wanted to do was put all mathematicians out of business. What he wanted was an algorithm that, given a statement in formal logic, would determine if that statement was true or false. This was called the Entscheidungsproblem, because it sounds a lot better in German. It just means decision problem. And what Hilbert was depending upon was the idea that logic is complete, meaning every provable statement is true and every true statement is provable. Sounds reasonable, right? Except, of course, in 1930, in Vienna, Kurt Gödel published his proof of the incompleteness theorem, and this meant that Hilbert was, to use a technical term, screwed. So what Gödel showed was that any logic powerful enough to represent arithmetic could encode the following statement: this statement is not provable. The way he did this is he used a clever technique called Gödel numbering to encode statements and proofs as numbers, which is why he depended on arithmetic. So don't worry about the details about how he did that, although it is one of the world's first functional programs. But think about this statement: this statement is not provable. Oi. Right? As soon as you have this statement written down, you are in trouble. Why? Right? So it's very much like what we heard with the liar's paradox, only now it's provability. So what happens? Well, if it's false, then it is provable, and you've proved something that's false. This is really bad news. You don't want to do that. So the alternative is that it's true. But now you must have a statement that is true but not provable. So that's not as bad, but it's still really annoying, especially if you're Hilbert. Now, as long as people thought that there would be a solution to the Entscheidungsproblem, you didn't need a formal definition of algorithm. You would just write down the algorithm that was the solution, and it would be like Justice Potter's definition of pornography. I know it when I see it. But if your goal is to show the Entscheidungsproblem is undecidable, then you need a formal definition of algorithm, so you can show that no algorithm is going to work. So the race was on. The first solution was proposed by Alonzo Church in Princeton. He came up with this thing called lambda calculus in 1932. And by 1936, he had used it to show that, yes, if an algorithm is what you can express in lambda calculus, then it is the case that the Entscheidungsproblem is undecidable. He actually did this by means of something else that was undecidable, which we now call the halting problem. There is the complete definition of lambda calculus, much briefer than those of you that use languages like C or Java. It's only got 3 constructs: variables, function definition, and function application, right? And it's the world's coolest programming language because it was defined a decade before one had computers. For many years, me and my colleagues have worked with functional languages, which are based on lambda calculus, and for many years, people in industry have managed to pretty much ignore everything we do. But of course, these days, lambdas have become very trendy. You have lambdas in C++, you have lambdas in Python, and you have lambdas in Java. So there's Duke, the icon for Java, looking very smug. Congratulations, Duke, you have finally caught up with where Alonzo Church was in the 1930s. So here we are, back to Kurt Gödel again. He came visiting in Princeton, and he thought that Church's solution was thorough. His precise words were, thoroughly unsatisfactory. So Church went to Gödel and he said, look, you come up with your own definition and I'll show that mine is as good as yours. And Gödel did. He came up with a second definition of computable, effectively computable, which he called general recursive functions. And this was actually written up by Church's student Kleene with attribution. And Church duly went off and he showed the 2 definitions were equivalent. And so he went back to Gödel expecting this would resolve the matter. And Gödel said, oh, my definition is the same as your definition. My definition must be wrong then. The impasse was resolved by this man, Alan Turing, at Cambridge, who of course came up with what we now call Turing machines. And again, he showed that that if Turing machine was your definition of an algorithm, that the Entscheidungsproblem was undecidable. And Turing proved his definition was equivalent to Church's and hence to Gödel's. What Turing did that was different was not the mathematics, it was the philosophy. He gave an argument that anything that a computer could do could be done by a Turing machine, where again, computer means a person following a sequence of instructions. And Gödel was finally convinced that all 3 equivalent definitions did capture effective computability. Philosophers often argue, is mathematics invented or is it discovered? 3 times, guys, 3 different independent definitions all turn out to be equivalent. That's powerful evidence that you've not invented something, you've discovered something, right? It's not just sports fans who are impressed by a hat trick. Kurt Gödel was 28 when he undermined the work of David Hilbert. Alan Turing was 23, still an undergraduate, when he undermined the work of Alonzo Church, who was 33, and Kurt Gödel, who was then an ancient 30. So to all you young people in the audience, please keep explaining to your elders when we are wrong. Okay, so now you've got the background, and we can start talking about the brilliant idea of propositions as types. So here is Gerhard Gentzen. He was trying to carry out what was called Hilbert's program, and he came up with a new way of writing down logic. Here it is. So we're just going to focus on, so this is called natural deduction. Gentzen, in his PhD thesis, came up with natural deduction, which is the main form of logic we use today. He came up with sequent calculus, which is the second most used formalism in logic today. And he also came up with using the upside down A to mean for all. So there's a little goal for all you PhD students. So here's, this is actually from Gentzen's paper, and we're just going to look at a fraction of this. So the fraction's having to do with implication and conjunction. So implication is that funny backwards C. It really is a backwards C. It's consequence backwards. And ampersand, which means and. And you can see that let's see, where's implication? Here's implication. And you can see it's exactly the same, except that Gensen wrote his letters in German. And then conjunctions up at the top there. So, whoops, other way. So what do we have here? The first line, so the first rule there, the rules come in pairs. This is the important thing. So on the left, we have rules with I, meaning introduction rules, and you have the connective, implication, or ampersand below the line. The rules on the right are called elimination rules, and there you have a connective above the line. So you can see A implies B on the left there. And what does the one on the right say, the elimination rule? It says if you know A implies B, and you know A, those are the two hypotheses above the line, and then below the line we have the conclusion. What do you know if you know A implies B and you know A? Hey, you know B. So that's how you make use of an implication. How do you create or introduce an implication? Well, it says, so those brackets around the A mean assume A. Don't prove A, just assume A is true. If you assume A is true, and from assuming A is true, you can get a proof of B, then you know A implies B. And the second line say, well, if you've got a proof of A and you've got a proof of B, you've proved A and B. And what can you do with that? You can do two different things. So the middle rule set on the bottom says if you have proved A and B, you may conclude A. And the other rule says if you've proved A and B, you may conclude B. Okay, are there any questions? All right, I will zip on, but do ask a question if there's something that's confusing you. I'm sure it will be confusing other people as well. So here's a little proof. It's a proof that if you know B and A, then you can conclude A and B. Now, this seems bloody obvious, right? Of course, if I know B and A, I can conclude A and B. But it would be nice to actually have a formal proof. So here's the formal proof. It says, okay, let's assume B and A. And on the left, we say, well, if we've assumed B and A, we certainly know A. On the right, we say, well, if we've assumed B and A, we can certainly conclude B. That's using the two different elimination rules. Now we've proved A and B, so we know A and B, and now we can discharge our assumption. So with no assumptions now, we know that B and A implies A and B. Now, the key thing that Gensen did that was amazing is he had the insight that the rules come in pairs and the pairs cancel out. And he used this to prove what's called the subformula property, which says that if you have a proof, you can always normalize it by applying these rules so that the only formulas that appear in it, so the formulas are our propositions here, are going to be the conclusion, the hypotheses, and parts of those, what are called subformulas, no other formulas. So I'll give you an example of that in a minute, but let's look at the simplification rules. The top one says, okay, I assumed A, I proved B, so I know A implies B, and I've also got a proof of A, so I can conclude B. But there's a simpler way of doing this, right? We don't need to assume A, we were just given a proof of A. So everywhere in that proof on the left that you have an assumption that A is true, just replace it by the proof you were given on the right that A is true. And now we've got another direct proof of A, another direct proof of B that doesn't use the formula A implies B. So we've got rid of a formula that doesn't appear in the conclusion or the hypotheses. Similarly, if from A and B you can conclude A and B, and then from that you conclude A, well, there's a much simpler way of doing that, right? Just, you've got a proof of A, just use that. So proofs can be simplified. So let's do an example of that. Here's a roundabout way of proving A and B. So let's say that somewhere I've got a proof of B and A. But we've just proved, right, that B and A implies A and B. So by modus ponens, I can conclude A and B. So we've got a roundabout proof. And notice this proof has formulas in it, like B and A implies A and B, that don't appear in the, so we've got two undischarged hypotheses here, B and A on the left, and some discharged hypotheses. the B and A, which has a little z on it, as discharged by the rule arrow implication, which has a z saying, right, this is the rule that discharges those hypotheses. So we've got two undischarged hypotheses, B and A a conclusion, A and B, and a bunch of other stuff, including stuff like B and A implies A and B that doesn't appear as a hypothesis or a conclusion. Can we get rid of it? Well, yes, because our second to last rule is an introduction, and our last rule is an elimination, so we can just do what I said and take those two places where we assumed B and A and replace them by the proof of B and A on the right. So it simplifies down to this. And once we've taken that proof on the right and moved it on the top, yes, we've now got two places here where and I is on top of and E. So we can simplify again, and now we've got a direct proof. This is a much simpler proof of the same thing. Now notice that when you substitute something into a proof, it might actually have more nodes in it, but it will always be simpler in the sense that you've gotten rid of a subformula. And you keep doing that till you've gotten rid of all the subformulas, and that always works. Why did Gensen care about this? Because it says, okay, well, just knowing that proofs could always be done in a direct way, that they weren't roundabout, that's kind of cool. But in particular, you can do the following. One of the formulas you have is false. And a logic is consistent if you cannot prove false. You really don't want to have any proofs of false sitting around. If you did have a proof of false, then what the subformula property tells you is the proof would look like false and only consisting of subformulas of that. Well, there are no subformulas of false, right? It's like, what part of no don't you understand? So it's very easy to look at the proof rules and say, okay, there's no proof rule that ends in false, and therefore you couldn't get it in any other way. So it gives a simple proof of consistency, among other things. Now, at pretty much the exact same time that Gensen was coming up with this new way of formulating logic, this was when Church was coming up with lambda calculus. Now, Church originally used lambda calculus as a kind of macro language for a logic. And it turned out lambda calculus is really powerful. In fact, it's so powerful, it let you write down the equivalent of infinite formulas, and with those, you had an inconsistent logic, one that could prove anything. So that was kind of bad. But he did write in his original paper, it may have uses other than its use as a logic. In particular, it turned out to be good for defining algorithms. But also, he wanted a consistent system. And to do that, he used the same way of getting rid of paradoxes that Russell used. He used a type theory. So in 1940, Church wrote down the simply typed lambda calculus. So here I've got terms of the lambda calculus in red and conclusions in blue. And as well as functions, I'm now dealing with pairs. You can also deal with things like record variance, and pretty much every data type you name, you can build up out of these ideas. But I'm just going to show you functions and pairs. So lambda xn, where x is a term, lambda xn is a term, it's a function. It's a function that, given a value of type A, returns a value of type B. So it's a function from A to B. And what does this mean? Well, x must be a variable of type A, and it must appear in some term n whose type is B. So lambda xn would be a function from A to B. And then if L is a function from A to B, and M is an argument of type A, well, of course, if you apply L to M, the result has type B. And a pair is built from two terms of types A and B, and gives you an AB pair. And of course, first and second extract, if you've got an AB pair, first would be an A, and second would be a B. So a very simple definition of a small fragment of simply typed lambda calculus. So here's an example of a program. Lambda z return the pair second of z, first of z. So what does this do? It swaps the elements of the pair. And so its type is going to be take a BA pair and return an AB pair. Right. So at this point, I'd like you to all reach under your seats. You should find there some rose-colored glasses. Please put on those rose-colored glasses. You will then only see the blue bits and not the red bits, and that should look kind of familiar. Right? So the blue bit of what Church did is exactly what Gentzen did. Now, it actually took a long time to see this, because the proof I showed you that of Gentzen's result, Gentzen didn't prove it that way. He had to invent sequent calculus to prove it. It's kind of ironic. Gentzen needed a roundabout proof to show the absence of roundabout proofs. But Pravitz, a little later, came up with the form of proof that I showed you. And then Church came up with this, and there are rules for evaluating lambda expressions. They're very simple. The first rule says if you've got lambda xn applied to m, what does that mean? Well, take the actual parameter m and substitute it everywhere for the formal parameter x. And what does it mean given an mn pair to take the first component? Of course, it just means return m. And again, if you put on your rose-colored glasses, you see that evaluation corresponds exactly to simplification of proofs. The one thing you need to know is that this process terminates. That was actually first proved by Turing, of all people. So remember, the hard thing about the halting problem is you can never solve it. It's undecidable. There's no algorithm that tells you if a given algorithm halts or not. But if it's in simply typed lambda calculus, if you've typed it and you're not using what's called the fixed point operator, that is unlimited general recursion, yeah, that's the idea that Gödel came up with, then you're guaranteed that it terminates. So we have functional programming languages where we include the fixed point operator, and you can write every general recursive program, as do everything a Turing machine can do. But we have other ones which are simply typed like this, and examples of such languages are things like Agda or the proof system in Coq, and those are guaranteed to always terminate. So the halting problem, which you think of as a very hard problem, is actually completely solved by this idea of types. And then here's an example. So here's the program that swaps two elements of a pair applied to a particular pair. And of course, we just substitute in the argument yx for the formal z, and we get that. And then we simplify again, and we get that. So notice what these rules are telling us is that as we evaluate a program, it stays well typed. So what have we seen? Propositions in logic correspond to types in a programming language. Proofs in the logic correspond to terms, programs in the programming language. And simplification of proofs corresponds to evaluation of programs. So it's not a shallow idea, it's a deep idea with a lot of structures. Propositions as types, proofs as programs, simplification of proofs as evaluation of programs. Ooh. You say, that's really cool. But hey, it's just kind of an accident that it happens once like that, right? Well, no, it's not an accident. Oh, so this is sometimes called the Curry-Howard isomorphism. So this is a drawing due to Luca Cardelli, illustrating the correspondence between types on the top and formulas of logic on the bottom. So the idea showed up many times in the 20th century. You can find it in the work of Brewer, Heiting, and Kolmogorov, the intuitionists. But it was noted by Haskell Curry. And then the form that I'm showing you really was clarified by William Howard, who then went on to say, well, wait a minute. If implication and correspond to these things, what do for all and there exists correspond to? And that came up with a new kind of type that hadn't existed before called dependent types. And these are the basis today of many proof systems. So it's often called the Curry-Howard isomorphism. It's often called the BHK interpretation. It's sometimes called propositions as types. Anything that's really important will, of course, have lots of names. So there's Howard's original paper, which was in fact published in a festschrift dedicated to Curry. So there's what I showed you, right? Propositions as types, proofs as programs, and normalization or simplification of proofs as evaluation of programs. As I said, well, fine, but it's just for this one particular logic. In fact, what I showed you only works for something called intuitionistic logic. It's just kind of an accident, right? Well, no. It works for everything. So here's just a couple of ways in which it works. And the interesting thing to note here is, for instance, the logician Hindley came up with type schemes, and the computer scientist Robin Milner came up with the type system of standard ML, which is the basis for the type systems used in all functional languages now, like F# and Haskell. And notice that, hey, a logician, it's now called the Hindley-Milner system, right? But a logician and a computer scientist independently discovered the same thing. There's something called polymorphic lambda calculus, which is actually the basic for generics in Java. And it was discovered once by the logician Girard, who called it System F, and once by the computer scientist Reynolds, who called it polymorphic lambda calculus. So Curry-Howard is a double-barreled name that predicts there will be other double-barreled names. Every good idea will be discovered twice, once by a logician and once by a computer scientist. And pretty much every functional language you can name has as its core the lambda calculus. That's pretty much the definition of a functional language. And interestingly, pretty much every proof assistant you can name, such as Coq or Agda or what have you, has at its core dependent types as and using lambda terms to represent proofs in exactly the way that we were discussing. So that goes back to the automath system of De Bruyne in the 1970s. Some people actually don't call it Curry-Howard, they call it Curry-Howard-De Bruyne. So it's a very powerful idea. And of course, just like any programming language, there are bits in all of these things. There are bits in all of these things that are completely arbitrary. But their core is not arbitrary. Their core is something that was written down once by a logician and once by a computer scientist. That is, it was not invented, but discovered. Most of you use programming languages that are invented, and you can tell, can't you? So this is my invitation to you to use programming languages that are discovered. So Turing's important contribution was philosophy, so I'm going to indulge in a wee bit of philosophy to conclude. Let's say that we tried to talk to aliens. We've actually done this, right? This is a plaque on the Voyager. And this diagram on the left is to try to where the show is relative to various pulsars. There are marks on that which are actually in binary, giving you the frequency of the pulsar. And of course, the length of the line is the distance of Sol from the various pulsars. And then on the right, there's a picture of some people. Now, if aliens were to look at this, right, the bit on the left, they would probably be able to work out. That's the length of the line is distance, and they could probably work out binary numbers, and that's frequency, and there's a little thing saying, oh, it's frequency of hydrogen. They could probably work that out. The thing on the left, well, that would depend, right, on what the aliens were like. If Star Trek is correct, then the aliens would look at the bit on the left and say, oh, they look just like us, except they don't have pubic hair. But if Star Trek's not correct, and aliens are really alien, they just might think that the bit on the right is some scribbles that they cannot decipher. It all depends. So some things you can work out easily, and other things you might or might not be able to. So let's say we tried to communicate with aliens in a programming language. So there's a movie called Independence Day, and in it they destroy the aliens by giving them a computer virus. And there is the computer virus. And if you look at it closely, you can see that it's written in C. It's actually a dialect of C that only has open brackets. So this movie came out in the mid-90s. How do I know it's C and not Java? Well, this was the mid-90s. That was before Java spread throughout the known universe. So this seems kind of unlikely, right? Whether it's C or Java, it's unlikely that you could program an alien computer using it, right? But what about lambda calculus? What about lambda calculus? Lambda calculus isn't invented, it's discovered. If aliens know the fundamentals of logic, if they know the rule of modus ponens, then they must also know lambda calculus. So if we sent them on a plaque a formula in C, I think they might have trouble deciphering it. But if we sent them a formula in lambda calculus, I think that is something that they would be able to work out. So lambda calculus would be more like the thing on the left that's easy to decipher than the squiggles on the right. So, right, we should call lambda calculus the universal programming language. Well, let's think about that for a minute. It's become common these days to talk about multiverses. This is from a play called Constellations, which has the coolest stage direction in it I've ever seen. It only has one stage direction. It says, a horizontal rule in the script corresponds to a change of universe. So this has entered our popular culture, and it's also entered science. So scientists say, why is the weak electron force the strength it is? If it was just a little bit stronger, electrons would repel, and we wouldn't have matter, and we wouldn't have life. If it was a little bit stronger, electrons would clump together, and we wouldn't have matter, and we wouldn't have life. Why is it the strength it is? Well, because we're in a universe where we can see it, so there must be matter and life, so that's why the electron force has to be. So they reason using multiple universes. And multiple universe might have something like different electron force, different gravity. That's fairly easy to imagine. What about a universe without logic, without modus ponens? I find that very difficult to imagine. So we really cannot call, I'm sorry to say it, but we can't call lambda calculus the universal programming language. Right? And the reason we can't do it is because calling it universal is too limiting. So in conclusion, right, what I'd like you to remember is that when you've got a tough job, you should think that this is a job for lambda calculus. Thank you very much, and I will now take some questions. Yes? Where can you get that shirt? I have tried many times to put this shirt online, and every time I've done it, the online firm has said, you can't do it, that's a copyright violation. So if you can tell me a way that I can do it, let me know and I will do it. Any other questions? Yeah. Oh, not just lambda calculus. They've ignored lots of things. Right, so the question was, I claim that industry has ignored lambda calculus for many years, and the question is, why is this the case? If you look at good ideas, like garbage collection came around in the late 50s, early 60s. It finally became prevalent in the mainstream community with the advent of Java. and even then many people fought against it. So it's like 25, 30 years, maybe 35 years before garbage collection got into widespread use. Even though we think of it as a very rapidly moving field, fundamental good ideas often take a very long time, 25 or 30 years, to be adopted, which I will rant now for a minute. In the UK, we're supposed to do impact studies to show the impact of our research, and impact must be an idea that was published 20 years ago and used within the last 20 years. So I want to use, Java makes use of generics, which comes, among other things, from the work of Robin Milner on the Hindley-Milner type system, and I helped contribute to generics in Java, so that's clearly an impact story. Well, no, because the original work by Robin Milner was too old to count. It was more than 20 years old. If you look at what happens in the development of logic, Boole comes along in the mid-1800s, Frege and Hilbert around 1900, all the stuff I showed you around 1935, and it was 1935 that Gensen and Church came up independently with natural deduction and simply typed lambda calculus. It wasn't until in late 1960s, 1969, that Howard wrote this down. It was just circulated as a Xerox note. It wasn't published until 1980. So that's like 45 years. It takes a long time for good ideas to get out. And so it's worth having a long perspective if you want to have the best and most interesting ideas, if you want things that are discovered and not invented. That was an excellent question. Thank you. It let me rant. Any other questions? Yes?
Do you think, so in the Curry-Howard correspondence, there's like logic and lambda calculus. Do you think that there are other systems that correspond to the same thing?
So the question was, in Curry-Howard, we have a correspondence between logic and lambda calculus. Are there any others? And of course, we saw a few others. Right. So on the left here, we have lots of different varieties of logic. And on the right, we have lots of different features of programming languages. By the way, there's one thing that's omitted from here, which is the most important one, which is distribution and concurrency. And of course, there are many, many different solutions to distribution and concurrency. What is the right one? Wouldn't it be great if there was some logic that corresponded to distribution and concurrency? That might give us a hint as to an idea that is discovered rather than invented. And indeed, linear logic on the left seems to correspond to things called session types on the right. And in fact, that's a major focus of my current research. So there's a possibility that we will be able to discover an approach to concurrency and distribution, again, that is discovered rather than invented. But that's still ongoing work. And of course, once we're done, it will then take another 25 years before people adopt it. So that wasn't quite your question, because these are all different varieties of logic and different programming features. Your question is, does it happen with other things? Well, yes, it happens with things like thermodynamics and information theory. Oh, is there a third column or fourth column? Yeah, people, so many people say that category theory is the third column, and that corresponds to both of these things. So yes, this actually goes deeper. There's some very nice paper by physicists talking about these correspondence because they get exploited in quantum physics. So yes, this extends through even to things like quantum physics. So thank you very much for that question. That's an important point. But there might be other things waiting to be discovered. Question?
Do you think there'll ever be a case where computer scientists will discover one of these correspondences before a logician?
Oh, brilliant question. So this fellow was noticing, look, the logicians always get there before the computer scientists. Will the computer scientists ever get there first? That's a very good question. I suspect the logicians always get there first because they've been at it longer. But for instance, linear logic was not discovered twice. Linear logic, when Girard came up with it, was actually published in the journal Theoretical Computer Science, because already this correspondence between linear logic and concurrency, this notion that there might be something there, was there at the time he discovered it. So in that sense, the two came together. And even, it turns out, John Reynolds had done something almost like linear logic just a few years before, called syntactic control of interference in concurrent systems. So some people refer to Reynolds coming up with this idea as, just before Girard, as Reynolds' revenge. Yeah?
Are there any probabilistic correspondences?
Oh, very good question. Are there any probabilistic correspondences? I suspect so, but no, I don't know what they are. That's something I don't know about, and I think that'd be a very interesting area of research. Yes?
What does this say about the impact of computer science on our understanding of knowledge in general?
My favorite question. What does this say about the impact of computer science on knowledge in general? Right? A lot of what we do day to day has arbitrary bits to it. This, I've tried to explain to you, is deep and not arbitrary. We are discovering things rather than inventing things. Clearly, that has to have implications everywhere. And there's a growing movement that says, look, the ways of thought applied in computing, the things that you guys are all good at, give us new insights into how information is structured. And structuring of information is not going to just be important for understanding how computers should be designed. It can also be important for understanding how the universe works. So this idea of using ideas of how information is structured to examine many, many different fields goes by the name of informatics. And some people work in departments of computer science. I actually work in a school of informatics. And I think informatics is a much better word to use. Right? Computer science, there are only two things wrong with it: the word computer and the word science. Right? Because it's not about just the computer, it's about patterns of information. And you don't put science in your name if you're a real science.